This one?
No, mute this one.
Yeah, it was muted. I think it had feedback between the two of these
Yeah.
ones.
It's your computer?
This one's muted. This one's not muted now.
Oh.
Okay, once you get started.
All right. Do you want to
Yeah, we'll get started.
run through it, I guess?
Yeah, I guess we'll go as fast as possible.
Do you want me to run the slide while you talk?
Assignment of the things. So I don't think there's anything to fantastic.
We'll go as quick as possible. So we have previously we showed 3 different options. I think we were looking at. We decided to go with the methanation of carbon dioxide to make methane. People will store and use hydrogen on that. What?
You have a sick or something? I can't hear you. Very.
Yeah, I'm not sick. It's my work finally made me get the 2nd dose of that vaccine. I'm, mask. Plus, so we're going with methanation of CO2. So next slide. This is sort of a mock-up of sort of what we designed. The idea is basically have a long channel. You bring water and CO2 into it, and then we're going to basically test whether we get methane out of it. So specifically what we're doing in our design is with the typical, this is called the Sabatier process. You first separate your hydrogen out by another method, and then you run it with the hydrogen gas with the CO2. This is called an in situ method, meaning the hydrogen is produced from the water at the same time as the CO2 is methanated. Critical difference between this and other in situ methods is previous in situ methods use really costly membranes to separate the hydrogen out to split the water. We figured, well, you need a nickel catalyst to activate to create the methane from the CO2. That can also be your energy source for the electrolysis. So in this case, we're going to have a bunch of nickel plates of nickel mesh that the water will be running, water and CO2 are running through, that are held at a voltage difference. It will split the water, and then the negative plate, hydrogen will move to the cathode, which will then react with the CO2 to make methane. So basically, again, the idea is because water is a polar molecule, it should split fairly easily. Based on the literature, somewhere between 1.25 and 1.8 volts is the potential you need to create across that gap to split the water. CO2, meanwhile, is a non-polar molecule and doesn't split at any reasonable potential. And so it should just be passing through because of the sort of pressurized, just a flow which is carrying in. And then again, hydrogen be collected with the cathodes, direct with the CO2 to make methane, which also is pretty much non-polar. It should just move to the exit.
So here's a quick estimate of material costs for this design. Nickel mesh can be a little bit expensive, but I found that a 100 millimeter by 500 millimeter piece of nickel mesh is about $85 per sheet, which should be, I don't know, depending on the diameter of the tube that we choose, should be enough.
Does the mesh size matter?
Yeah, certainly the
because of the
closer
surface
parent, the
area.
better.
Yeah,
The surface area.
yeah.
Mhm.
So the containing pipe to hold everything in place, we were just figured we could get like a stainless steel piece of tubing from like Home Depot or Lowe's or something, and that's about $3.36 per foot. The orange pieces there that are holding the nickel are going to be 3D printed. And so 3D printer PLA is about $15 to $20 per kilogram. Probably won't use that much. And then the wire going through it is about 30 cents per foot. Another cost benefit that we kind of talked about last time was the heat transfer from the solar panel to provide the electricity for this system. And we found a quick difference between a PVT, like a PV thermal panel versus a conventional PV panel. At the same wattage, it's about $100 more. So here is production costs for transferring CH4 to H2 at the pump. I found this from the Department of Energy. It's a little bit hand wavy, but the production cost ends up being about $2 per kilogram, depending on the inputs into the
What's
system.
GGB again?
I think that might be a typo. I think it might be
Kilogram?
kilograms. Yeah. So, but you go to the next slide. The last slide was just production cost. But when you're producing at the pump, you need a store because you can't produce it fast enough to deliver it at the same time. So we have levelized costs for compression and storage, and it brings the total cost to about $3.80. But this was using their feedstock costs, but we plan to use our own feedstock from the previous design. Next.
All right. So I added this in as like a kind of a goal. So what this is saying is, show. Okay, right there. So 1 gallon of gasoline is about 2.75 kilograms. And energy in 1 kilogram of hydrogen gas is equivalent to about the energy of 2.8 kilograms of gas, as you can see over here. So it's not exact, but almost 1 gallon of gas equals 1 kilogram of H2.
Yeah, explain to me why is it 1-to-1?
It's almost 1 to 1.
Okay.
So one gallon of gasoline is 2. Yeah.
Sorry.
And the reason I decided to include this is, as Brad already talked about, one of our biggest customers would be the automotive industry. And a goal to try to beat is the gas costs, which that's what it currently is in Utah. So if we can get it below that or about that same cost, then switching to hydrogen can be more feasible. In terms of energy, converting from methane back into hydrogen, it's a very endothermic reaction. It takes a lot of energy to do it. Per mole of, I guess right here, 206 kilojoules per mole of methane. And from that, we get about 4 moles of hydrogen gas. If we include the water reaction as well with CO, which is doesn't require energy to do that. We can just capture the CO and move it directly in there.
Where's
Kind
the
of
water from? I forget that. Is that part
Just-
of the electrolysis?
Yeah,
Is it the feed?
That's the feedstock.
it's the
Feedstock
the
is water.
feedstock is
Yeah.
water. Yeah. So just kind of estimating at 65 to 75% efficiency, the energy costs. If we do not subsidize it with solar, if we just use the average US energy cost, it would come out to about this per kilogram of H2. But that's just the conversion from the methane to hydrogen. Obviously the price increases depending on where you get the methane, how you create the hydrogen. But it kind of gives us a little bit of playroom if we can get it down to that cost, and we want to beat this gas cost. But
There's probably some federal subsidies as well, I assume, for hydrogen.
Mhm,
sure.
yeah. They just did a thing at the Capitol a few days ago. There was an article on KSL. There's a local hydrogen company using wastewater. Yeah.
Great. Let's see how we can do that. One thing which I would recommend to do, again, was. Your system level simulation, you may want to do it a little more. I like the cost analysis, but you should also do the technical analysis and you want to do that next time around. That would be my.
Okay.
feedback. And if you have, if you want to talk through it with me separately, you can do it if you want. You don't have to, but that would be my suggestion for the next one. Otherwise, I would. Yeah, I mean, of course, this will also feed into the canvas, so thinking of that as well. Great, well, thank you.
Thank you. I think that's Nathan's.